It's my great pleasure to introduce Robert Bradshaw. He's going to talk about how to be a Cython developer.
Okay, so when I was preparing for this talk, I was thinking about Cython code base and all that kind of stuff, and I realized that Josh pretty much covered everything. But I'm going to try to come up with things that didn't cover. Then at the end, I'm going to leave a little time for questions. So first thing, just that came up recently. Someone was like, well, what exactly is, someone's actually trying to convince Greg, well, why don't you join Cython almost? And he came up, well, you can think of it as kind of...
Somebody was trying to convince him of that.
Yeah.
Literally.
And he said, you can think of it as like Pyrex unstable or Pyrex experimental. And that's actually not really how we think of ourselves. We think one of the reasons that we have Cython is because it was really hard to get the changes that we wanted and we thought were important into Pyrex. And so I think the biggest advantage that Cython has over Pyrex is that it has a much more open development model. We're wanting feedback from other people. We're wanting other people to write patches, to write features, and put them together. And I think this is going to be its biggest strength moving forward. So in terms of the development model, it's mostly modeled after the Sage project, and that's just because that's the open source development that I've been most involved in. And this is going to be one of the things that I'm sure we're going to talk about in development days in terms of how do we want to set up, for instance, patch refereeing and that kind of thing. So, but the important parts, I think, is that every copy of Cython comes with the Mercurial repository. So if you want to learn how to develop Cython, the first thing to do is get a little bit familiar with Mercurial. And it's a pretty easy to use distributed revision control system. And so what you do is you edit your files and then you commit to your own local repository. And when you have something that you think is good enough, it might just be one patch, then what you do is you make a track ticket and you post your patch on that track ticket. And I think that just in terms of size, we're more friendly to bundles than patches than Sages. Because with Sage, the problem is if everyone posted a bundle, then about half your commits would be merges. But with Cython, one of the things is, at least currently, there's a lot of interdependency. It's easy to change one thing and then you have to change a little thing here and then change a little thing there. And so if you just post patches, lots of times, you'll be like, oh, it doesn't work. Oh, that's because I forgot to post this patch over here that this relies on. And also with a much, at least currently, smaller developer base, it's not as hard to use bundles. So another thing is, so like I mentioned, we have this, this bug and feature tracker. We're using, as of, I guess, this month, Track, which is the same that Sage uses. And what I did is, if you have a Track account on Sage, I copied the HT password file over, so now you have a Track account on the Cython Track as well. So, and then there's also, of course, people who have just a Track account there, they don't have one on Sage. Another thing that we try to do with the development model is when someone has a question, and if that question gets answered and they say something to the effect of, well, is this in the documentation anywhere? My first response is, I don't think so. Why don't you add it to the wiki? And of course, we also have official documentation that's being worked on. But we try to really promote people getting involved by trying to add it to the wiki. And then the other thing is we have automated testing. This is a little bit different than the way you do it in Sage because it's very hard to test a little component. Sage is the perfect example of doc tests because when you start up Sage, you have this big environment and then you have an interactive command line where you try things out. And with Cython, you can say, well, let's see, does my code that generates the actual, the piece of code that generates the temporary variables for a for loop, is that working correctly? And you can't just say, well, what's an interactive session I could do that can test that out? You have to create this, create this parse tree, and then do some stuff on the parse tree to get it ready to the point where you need to allocate the temporary variables. And then you test to see if it allocated the temporary variables right. And so most of the testing for Cython is actually, we have a big directory of PXD files. And so the testing is try to compile these PXD files and then run them and see if they work correctly. Which isn't as direct, but we try to make, little PXD files that say this thing is testing this specific feature. We're testing casting from Python objects into ints.
Why are they PXD files instead of PYX files?
PYX files, sorry.
Oh.
PYX,
Okay.
sorry. Yeah. So it's a directory of PYX files.
Are they inherited from PyX?
Some of them are. So Greg's original testing mechanism was that he had a bunch of files, and he would actually do a diff on the C output.
Yeah, and then automatically update his.
Yeah.
Yeah.
And so now,
and then just
now
look
he's
at it by
actually-
eye and see if it.
Yeah, he's using a Mercurial to track his changes now, which is really good. But the signal to noise ratio is really hard because you'll have a diff that's, hundreds and hundreds of lines of how the C output changed.
I see.
And the actual C output is a very chaotic function of the Python input. Because, for instance, you have a bunch of temporary variables that you're using, and they're just numbered sequentially in the order that they were asked for. So, if you change something slightly, it may bump all those off by 1. So we actually try to see if the code compiles and runs correctly rather than comparing C output. And then, so all of this, I'd like to have a talk at Dev Days in terms of like, how do we want to do this? Because development is increasing at a very rapid pace. So here, for instance, is total volume of emails. And I don't have data before. This is when we switched over to the new email list.
What are your horizontal units?
So this is months. So this is actually January, February, March, April, May. Well, May up until now. So we still have, a week's worth of
Are you
emails
ahead of
to go.
Sage Devel right now?
What?
I bet you are. I bet you're ahead of Sage Devel right now.
Yeah.
Easily.
Yeah.
Because it seems like I get way more messages from.
This is actually this right here is in kilobytes, which was just the easiest stat to grab.
Kilobytes? What the hell?
And
what about
this is
number
the
of
count,
messages? Oh, okay. And you're probably behind.
which looks remarkably similar. I was
Yeah.
actually astounded. I guess the average email size is very consistent.
Yeah.
But in any case, you can see that it's greatly increasing in size. So it'd be nice to have some kind of a procedure, for instance, of right now in Sage you have with patch needs review, with patch positive review, and one person closes it when it's actually merged into the main thing. And one of the things that'd be nice is if the new version of Track has a release candidate now. And it'd be really nice if we could start using that soon, because that actually automates, you can set up custom workflows.
I think we should also include Track in Sage, because it has I think it has almost no dependencies that aren't in Sage, and it takes like 10 seconds to install. So
Yeah.
There's that one clear silver thing or something, but I know it's only like 10 seconds to install now.
Yeah, it's an
So-
optional S package,
Yeah.
I believe, so.
Yeah, I made it up, but I think it would be a useful thing to have in the core of Sage, because just like the wiki is like sort of a critical basic thing that's really useful for working on anything,
Yeah.
even on your own projects at home. So,
Yeah.
maybe, I don't know, I'll probably bring it up for voting, but pure Python things are usually pretty easy to get in. But it's mostly such.
So,
And start with the new release. Have you actually looked at how the workflow stuff works? Is it any good? I mean, it's possible it sucks.
yeah,
just
I
'cause it has a
looked
good
at it
name.
I looked at a bunch of things talking about how they were going to develop it, and it
Okay.
sounded really good.
Is it kind of like with patch needs review, but done much more in the system, or is it totally different? Or
So right now, basically, it's extending the system. Right now, the workflow is new ticket, assigned, assignment was accepted, fixed, and like that's
right.
kind of, and there's a, it's
Or invalid.
basically you can view it as a finite state machine.
Uh-huh.
And right now, the states are fixed with couple of
With
end
patch needs
final
review as a
states.
state. Yeah, I see.
So yeah, you have with patch needs review and
I see.
yeah,
It bounces back and forth. And
Yep.
accepted is.
accepted as one of the states. So.
Yep, got it.
So, kind of in terms of the goals, the high-level goals of where Cython's, where I see Cython going is the biggest disadvantage of Cython right now is it doesn't support all of Python. And I think this is, for instance, the goal that's keeping us from doing a 1.0 release.
What goal is keeping Greg from doing a 1.0 release? Because he doesn't care about this goal, but he doesn't do a 1.0 release either. Any thoughts?
I don't know that he actually has a goal. I think
That can keep you from doing a 1.0 release, having
Yeah.
no goal.
I'll say, I think he has a lot of goals, a lot of things he'd like to do, but I think the set of things he'd like to do grows faster than as he does it.
I see.
And I don't imagine that he'll do a 1.0 release until he's done everything he wants to do. Which is why it's been sitting at 0.9 for several years.
Yeah. Okay. But you would, if you did these things to fully support Python 2x and 3.0, you would feel like maybe a 1.0 release of Cython would be reasonable?
Yeah.
Cool. That's a nice, clean, sensible goal.
Yeah.
Would it be tested by, could it be defined by something like being able to compile the Python test suite?
Mm-hmm.
Cool.
Yeah.
Okay.
And yeah, so, and implicitly in here is the assumption that, well, I'll get to it later, that Cython is more of a Python compiler than a tool to write extension classes.
Hmm.
So, so the things that are missing, we need closures, and a lot of stuff depends on that. That's kind of the biggest gaping hole.
Why are closures called closures instead of something else?
I don't know.
Just somebody decided to call them closures one day.
Yeah, well, somehow you enclose things, I think.
Why aren't they called enclosures?
I don't know.
Okay.
Yeah, it's an old term going back to Lisp, I think. So.
Got it.
Yeah, and then the with statement and decorators, and there's some peculiarities with scoping. For instance, in Cython, if you use a local variable before you assign to it, then it has the value none. Whereas in Python, it will be an error.
Hmm.
So.
But wait, don't you have to explicitly declare the local, or you mean a Python local variable?
Python local variable. Yeah.
That's scary. Why is that? That seems terrible.
That's because that makes it so you don't need to check every time you use the variable whether or not it's been defined yet.
I see. And probably the Python interpreter does.
Python
so basically it
interpreter
makes
does.
Cython a little
Yeah.
faster.
So, and that one in particular will require some control flow analysis.
Yeah.
Because what you want to do is you don't want to bother checking if you know it's been assigned to. And it'd be nice, for instance, if we could throw an error compile time if it knows you're trying to use it before you've assigned to it. So.
But then you wouldn't know if it was assigned outside of the scope before
I thought
you ran it.
I thought you threw an error when you used a variable that wasn't defined.
Not in Cython. Oh, if you use.
You do in Cython.
So the thing is, you can have a local function.
Yeah.
And I can say print x, x equals 3.
Oh, I see. If you didn't say x equal to 3 after print x, it would be an error.
It would be an error because it says I don't know what this is.
I see, but
So
because you write x equal to 3,
yeah,
because you wrote x equal to 3 somewhere,
uh-huh.
it decides that anywhere you put print x, it's okay, because you declared it. You've used it
Yeah.
somewhere.
Yeah, so it knows what it is.
It's
It
just
just
out of
doesn't
order.
have a value yet.
I see.
And rather than having a null value, which would be a seg fault, it gives it none.
Huh. That's weird.
Yeah.
Okay.
So this has to do with just the fact that it's more difficult to decide these things at compile time versus at runtime. What you do is you just go
Yeah.
through and you're like, oh look, it doesn't have a value yet.
That could be ridiculously hard, because
Yeah.
it could be in a for loop, in an if statement that involves, if the Riemann hypothesis is true, then set x equal to 3.
Yeah, yeah.
So,
And so I mean, there's going to be certainly
or some random number equals 7, set x equal to 3. So you
Yeah.
just don't know at compile time whether that variable will ever be bound, or when.
so what you do is you can have an indeterminate state where you say, I don't know if it's bound,
Yeah.
you need to do a runtime check.
Right. Yep.
So the other goal of Cython is to be able to write optimized code without using the C API directly. So for instance, indexing into lists, or doing append, or doing math.score root. These are kinds of things where you don't want to have to, where there's an obvious Python C API thing, and you don't want to have to force the user to know the C API to be able to get fast stuff. And most of the optimizations in Cython are of this form. For instance, indexing into lists. It used to be either you had to know the Python C API to index into lists, and then grab the element out of it and do a PyIncref. Or you would do it the slow way, and you do L bracket I, and it would take I and then turn it into a Python object and call the generic get item method and all that. And then the other goal is eventual inclusion into Python. And I think the model for this is looking how C-types did it.
Mm-hmm.
And I think also C-types is interesting because if we want to be able to compile Python code, For instance, you don't have to make your thing a PYX file. Maybe you could point the Cython compiler to a Python module and just have it compiled. It would be interesting to use C types to be able to declare what types of variables are. And then also the interesting thing that is there, what you could do is you could run it as a Python module using C types. And then once you got it working, you can say, okay, now I want to compile it. And it would statically declare the types to be whatever C types they were.
What about, I guess we never talk about this at all, but OCaml, I don't know if you know about that language at all.
Just
it's an ML implementation that's object-oriented, but it's weird because when you type at the interpreter, it compiles automatically without you knowing it, sort of like built into how the thing works. It's like when you hit enter, it compiles the line and then runs compiled code. So another thing you could hope to do would be to have something that feels like you're using a Python interpreter, but every single line of input is compiled and then run. And I mean, part of this is, it's really tricky, but that's kind of like what you wanted when you were using Cython in a whole bunch of different notebook cells. You wanted them to all be compiled and run in somehow the same namespace with access to the C data from other places. So it's sort of like, it would be probably, since it is done in OCaml, and you want to compile arbitrary Python, and it would obviously be really useful. I mean, if you could use something that feels just like Python or Sage, but there's a little bit of a delay after you hit enter, but it's way faster. That would be pretty neat. So just throwing that out there as one of the other like possible goals that nobody ever talks about, but maybe they should, because it is done in some places. I mean, be neat. And actually, I mean, Tom pointed out, you could imagine putting the notebook in Cython mode and just doing that, but it's really hard to get access to the C def stuff in the other cells because they're completely different shared object libraries, and their locations when they're built are in funny places. It's only just and the names are fixed. And the names are that one. I'm sure that can be fixed, but anyways, just
that's an interesting thought. So
what about better debuggability also?
That's definitely something that I'd like to see too.
And profiling also. So for example, people, what if you have a cdef function with a whole bunch of C code in it? Since you've written a compiler, since Cython is a compiler, it could compile an instrumented version of the Cython code and give you better information about what's going on benchmarking wise.
It would be interesting, for instance, if you could give all the information that PDB would need to step through it line by line.
But also profiling. I think it would be super useful to have good profiles of what happened that are like at exactly the right level of detail for somebody thinking about the Cython code. Instead of the C code. And I think having the compiler insert instrumentation in would that be easy to do or hard?
It would be easy. I think it'd be easier to do profiling information. The hard part would be trying to do, like the interface between GDB when something really goes wrong at the C level and Python.
I'm thinking mainly about profiling information.
Okay. But definitely better profiling and debugging is, those are non-optimal now because you have great profilers and debuggers in Python and you have ones in C. But kind of this hybrid between both of them is difficult. And I think you want to use the Python tools, not the C tools. So.
When I gave my Sage talk at SciPy 2006, that was one of the topics that came up at the end when I talked about SageX. What about debugging it and profiling it? People always worry about that.
I mean, the print statement method still works just fine. That's one great thing about it.
At least that's the one invariant method.
But that doesn't help you profile.
It does actually.
Well,
it's just
a
lot of work.
Get the time.
It does work.
So there's this URL here that kind of holds the enhancements, and some of them are Cython enhancement proposals.
SEPs.
SEPs.
Are they also SEPs, like in Sage?
So kind of in terms of the high level goals, one of the things that kind of comes up a lot, and at least at this point, I think it's important to realize we're not trying to create a new language. This is because the difficulty in using Pyrex and Cython is because of the difference between Python and Cython. And so it's much more important to narrow this gap than to say, oh, here's a feature that I wish Python had. I'm going to add that into Cython because I can.
There's been a lot of people wanting to do that.
There have been a lot of people wanting to do that.
Fight them off tooth and nail.
Yeah. And I think first, certainly, not until we support all of Python should we look at adding new features. And then at the other end, I think if we want to do this, it might be worth having a Cython++ that say has all these extra features, but you want to make a language, adding features increases the learning curve to using that language. And then the other thing, so I think the primary difference between Python and Cython is types.
And it makes the language harder to read.
It makes the language harder to read, harder to learn, yeah. Harder to understand. So, so static typing, the fact that you can declare a type at compile time is the difference between Python and Cython. That's what makes it be able to do everything. And I think most stuff should be motivated by this goal. And you say, well, does it help us with this goal? And that's what allows you to write C code. That's what allows you to write fast loops. And that's actually an important thing to keep in mind when you're looking at the Cython compiler and trying to code with it. You think, well, it's Python, and the only thing it's doing more than Python is keeping track of types. It's analyzing what types things have. It's making sure types match up. It's coercing between different types. And that's kind of where the complexity is of a Cython compiler on top of just the Python compiler.
Is it going to be a coercion model? Have you thought about that?
Seriously,
I mean, because you have all these automatic coercions in Cython.
Yeah.
And in Sage, you also designed a coercion model. Is there any connection at all, really?
A little bit. The types in the programming language are much shallower. You don't have this notion of you have an element with the rationals and a polynomial over the integers. What type is there somewhere? But yeah, there is some similarity there. So then the other thing that's come up on the discussion list a lot are these things called transformation visitors. And this is kind of something that's representative of a higher level. Is right now, a lot of people who are new to Cython feel that it's really hard to really get into it. And the things are very, very tightly integrated. Like if you change something here, like changing the parser to do something different, you're like, well, do I need a new node that will handle that thing? And then, then what about its subnodes? They need to have extra information. And so there have been several suggestions to kind of take things to the new level of using these things called transformations and also moving to a visitor model. And I'm not sure if, one thing is, these look like they have advantages, but we don't want to do a whole rewrite of the system to do. That would probably be more of a disadvantage than an advantage. So the idea of a transformation is you have, for instance, the with statement. So this is a new construction in Python, I believe it was 2.5 and enabled by default in 2.6. The with statement.
Yes, that's true, that's new.
So the thing is, right here, the normal way about going about doing this, would you say, well, we need a new with node that can handle this kind of a thing here. And the idea of transformations was, what if we said, and this is actually in the Python enhancement protocol, that you have something like and this is simplified a little bit.
Is this like the preparser? The Sage preparser, basically?
Well, except for it actually operates on the syntax tree, not operating on the strings.
But still, I mean, the Sage preparser could be rewritten to operate on the syntax tree. Oh, no, it actually, that's wrong.
Yeah.
That's not true.
Yeah.
It serves a similar role.
It serves a similar role.
Right, but it's definitely not operating on the same
Yeah.
tree. I see.
So the idea is that it actually, it transforms this structure that the parser gives you into this, well, there's an except. And then finally,
because that's just the definition of width in Python, basically.
exactly. And so what if instead of implementing everything for the width node, you just said, well, we're going to have a transformation that takes this, outputs this, and then everything goes as before. So that's the idea of transformations. And there's a lot of things you could do with transformations. For instance, decorators could be implemented mostly as just a transformation. And
yeah.
So
can you say briefly what the with statement does?
Does that?
Yeah. So the with statement says this is an object such that I call an enter method that might change some global variable, but I want to guarantee that whatever happens, I can clean up after myself.
Okay.
And so the idea is that you call enter, and no matter what happens here, exit is called.
Have you ever used the with statement in any Python code you've ever written? Maybe you can give a more concrete example. I did once.
I have used it before, but not very much. A good example is, for instance, with an open file, do a bunch of stuff, and then this thing here would close the file when you're done.
I used it in with polynomial rings or other objects in Sage. You're not supposed to be able to change the generator names, like the variable names are immutable for parents, but there is a way to do with the variable names changed to something else, and then you put code in. I use that for printing, like when I wanted to print a polynomial and have the variables appear differently for some reason.
Yeah.
So it's good because you can preserve some sort of invariance, but be absolutely guaranteed that once you leave the block, the variable names get changed back. So, and then there was a lot of discussion about using with for implicit coercions in some context, I remember. I don't know if anything ever happened with that.
It's needs to sit on top of the model, but it isn't quite there yet.
Okay, but with is the sort of thing that might be really useful for saying
so
like
with this embedding of the number field into the complexes, do a bunch of stuff, and then at the end the number field forgets its embedding.
Right.
Yep. So then the idea of the visitor pattern is, so right now everything is recursive. So for instance, when you have a function, to compile itself, then it goes through and says, okay, each statement in analyze your type. For instance, to analyze the types of an if statement, it just goes through and analyzes the types of each of the substatements. And that goes through and analyzes the types of each of the substatements, and so on. And this is really good for something that you need to do on every single node. But for instance, for optimizations, like if you want to say optimize a for loop, if you want to just write a little code that optimizes a for loop, you say, well, where do I stick that? Do I stick that inside one of the for loops method that's already going to be called? Or do I make a new phase called optimize for loops that recursively descends down everything and only does something if you're a for loop? And so neither of those seem very ideal. And so the idea of a visitor is you have an object that is called the visitor. And what you do is you say act recursive. So let me try to explain this better. So the node and then what you do is this would be for the for node. So every method has a visit function. Every node has a visit function that visits the subnodes. And the thing is, all the information about what the visitor is doing is encapsulated in this visitor object. And so it recursively descends down the tree, and the visitor object gets to visit, it gets to analyze every single node, and potentially do something if it wants to. And then the nice thing is then you can make several visitors, you can choose what visitors to have. You can, for instance, have optimization visitors that do certain transformations, and you could compile your code with them and without them and compare the differences. So there's actually, the Wikipedia article on visitors is decent to kind of get an idea of what visitors
It's just a standard compiler idea? Or what?
It is a standard compiler idea, although it's a fairly recent compiler idea from what I understand.
What about transformations?
Transformations, I think, are really old. Yeah.
Okay.
I mean, you can, on a big level, you can view the whole thing as a transformation. It's a transformation from the original parse tree to a list of assembly instructions for a specific processor.
Okay, right. Compilers are transformations.
Yes.
I see.
But the idea is that you could represent this more explicitly than just in the code.
Mm-hmm.
And both of these are, the idea is to reduce the dependence between the Python code and the C code. So kind of now there's a one-to-one correspondence. And really you want to be able to generate Python code, like have it transformed into some C code that might not be a one-to-one correspondence, like here. You know, there's this extra code that gets generated here. Or for instance, with inner functions, well, the function doesn't actually get defined inside the other function. It gets put somewhere else. So, but both of these are kind of in the experimental phase. And there are transformations, but they might change before they get really useful.
You mean, so Doug has coded up some of this?
So he has coded up, and it is in the release.
Wow.
So
Cool.
that was the first thing he did.
Wow.
And they're really cool.
So are these transformations still change? Is this still, like this thing here would operate on the source code, not the parse tree?
No, so this would operate on the parse tree. So the parser would export a with node. And then you'd run a transformation that turns a with node into the tree that corresponds to
so
this.
You still have to have a with node, but it wouldn't actually have a generated C code or something.
Exactly, yeah. The with node would only be kind of a storage place, but it wouldn't have to do anything.
Placeholder, but it would, right?
Yeah. Which of course, I mean, when you think about it, if you were to implement a with node,
That's what you do.
it would have a lot of redundant, code with the try finally node. The try finally is not necessarily trivial to write. So, so there is some work that's going on to try to make it so that things are more compartmentalized and modular. And unfortunately, there was a summer code project that didn't get accepted that was actually going to look at taking the actual another parser that had a lot more support for this kind of stuff and putting that in the back end. And that may still come, but unfortunately it didn't get funded by Google. So, so for instance, for a concrete example of if you wanted to hack on Cython, so the first thing that you would want to do is really understand the feature that you're trying to implement. And so usually a good place to do that is, if it's a Python feature, then you look at the Python enhancement protocol, or proposal. And there's one for all the new features that they've added over the years. And if not, then you really want to hash out, well, what does this actually do? And so for instance, here I'm looking at decorators. And so I'd go to this page and I would read this entire page and see, well, what do decorators do? And it's a pretty long page, but you want to really understand, stuff like, okay, this is equivalent to this right here. So this is what I want to be implementing. So then what I'd do is, the next thing is I'd say, well, do I have to modify the lexicon? Like, does the lexicon even handle this kind of stuff? So, for instance, I'd say, well, I don't even see an @ symbol in here. So obviously the lexicon isn't going to be able to handle this @ symbol.
Robert?
Yeah.
One question, something that I think would be useful, which is probably hard, but like it'd be interesting if there was some tool which could let you could give some source code and it would produce like some representation, sort of here's the parse tree that's, this is how it's going to be parsed, and this is the node that's going to be produced if you feed this in.
Okay, yeah.
Or
yeah.
I don't know how you, suppose you were trying to do this and you say, oh, I'm going to modify, I'm going to add @ to this lexicon. And then you want to see, did that work here? Like, how do you?
Yeah, so, well, there is actually a transformation. It's kind of like a visitor, and the only thing it does is it prints out the tree.
Okay.
So that's very handy. But this right here is before you even have a tree.
Right, yeah.
So,
Okay.
although you could try putting at in the source code, and at some point it will throw an error, and that'll be a good indication to where it's supposed to be able to handle something. So, so one would, for instance, probably make a punctuation. Right here, one would add at to that list. And then it would accept at as a punctuation, and your parser would return that as one of its tokens. And then what you would do is you'd say, okay, now we did the lexicon, what's the next step? And of course, these aren't, where's that? These aren't going to be required for everything, but you say, okay, now we need to modify the parser. So we look at the parser, and we would say, well, where does this decorator come? Well, this decorator is a statement. So this function here says parse a statement. And you see this huge list of, things right here. And you say, you figure out, well, where in this big if-else list would I say, if I have an at symbol, then parse declarator. And so what you do is you'd add that to here, you'd add a parse declarator function, and then you say, well, what am I going to return? Well, now what you're going to do is you're going to have to make a new node.
I noticed with statements are there.
They are actually, yeah.
Are they implemented now?
There's the with GIL is a special term.
Ah, right.
Yeah.
So that's the only use of with.
That's the only use of with, but it means all the parsing is done.
What is
I
this?
see.
Yeah.
The global interpreter.
With the global interpreter lock. It means surround this code by grabbing the interpreter lock. And then releasing it.
Relevant for multi-threaded programming.
Yeah.
Is it only relevant for multi-threaded programming?
Yes.
With skill. Yeah.
Yep. Otherwise, you just always have to go.
Yeah.
So, and then what you do is, you'd have to add a node. So here's, the nodes file.
I saw my name there. Why is that there?
Where?
I see William
Oh.
Smith.
Relative position. This was the code function you wrote.
Oh, cool. That's the thing that he didn't accept.
Yeah, started the whole ball rolling.
Yeah.
So, so you'd write a node, whenever your node does, and your node would probably have a body, or whatever, a function, which is the function that it's accepting, which is the one that occurs right under it, because it's a declarator. And then in that node, you'd have to write, well, the node, what does it declare? So if I write at say, so here's my declarator that I'm trying to parse. Well, does this statement here make any declarations? Well, first I'll say, well, what does the parse tree of this look like? That's just a useful exercise. So it's going to look like I have foo is this is the declarator node, and under it I have, well, let me write. This is the I'm not going to be completely correct. The basic idea is I have this node, the decorator node foo, and one of its only child happens to be the function span. And the children of span has the arguments, and then it also has a body. And what does the body have? It has a return statement. And the return statement has the expression minus like that. And so this is the structure. And so you say, well, what is, if I'm looking at this node here, is anything being declared? And at the end of executing the statement, you have a new variable called span. So you have to say, I'm declaring for the step of the analyze declaration step. At the end, you'd say, well, I need to add something to my symbol table that says, after executing the statement, you have a new symbol, span, which is a Python function taking 2 arguments. And then, for the type analysis phase of things, this doesn't really analyze any types. There's no type analysis going on here. If we were to support this for CDEF functions, then you might have to do some type analysis. But as it stands, there's no real type analysis, except for you have to do type analysis of the body of this function. And then for the code generation, what you would do is you would look at this Python enhancement protocol, and either through transformations or directly, you would output the code corresponding to this, of actually creating this function and then passing it through these decorators. And so this statement would be the statement that actually gets executed at runtime. So that's an example of how you would actually implement something in Cython, implement a new feature. So, so are there any questions on that? You all feel comfortable implementing the decorators now?
Is that a really
Yeah, no problem.
pop quiz at the end? Get out your laptops.
So,
Can you maybe after this give an example of like for analyze types? You're just consistent about.
yeah, I can
There is
actually
an
do that now,
option.
because this is my last slide. So I'll just give an example now. So say my function looks like that. So what would happen is you would have your hook tree, and it comes down to, this would be well, I'm going to write it like this. So this has several attributes. The operator is minus. The left argument is x, and the right is y squared. Of course, this is a tree in and of itself. And so on the analyze types, what it would do is it would say left, analyze types. And it would say my type is a Python object, because what I did is I looked up x in the local variables table, so on parsing these arguments, it will add the x and the y to the local variable table. And so here it says I looked up x in the local variable table, and it tells me that I'm an object. So it says type of the left-hand side is an object. On the right-hand side, it will say analyze types of y squared. And analyzing the types of y squared will get, I'm just going to simplify this so we don't have to do another recursive level. Analyze the type of y, it'll say it's an int, and it's an int. By the same reason I looked it up in the table as a variable there. I know it's an int. Now what will happen is it'll say, now that I know the types of these two times, in this specific case, it has, well, let's actually look at the code. It says, is either one of my things a Python object?
Wow, it's like the coercion model.
It is. It's a lot simpler though, but like there's not this
Yeah,
dynamic thing going on.
because that gets taken care of by the actual function that gets.
Yeah. So this is going to be a,
I guess it gets pushed off to either Python or C to decide what the interpretation is.
yeah. So here is the analyze types. So we just did this step. Operand 1, analyze types. Operand 2, analyze types. Then it says, well, is PyOperation? Well, that's right here. Return, is this side a Python object or is that side a Python object? And since one of them happens to be a Python object, then it executes this one, right, this line of code here. Course operands to Python objects. So what that does is it takes this thing right here, and it turns it into a node in the tree that corresponds to taking this thing here and coercing it into a Python object. And so now what we do is we have two compatible things. And this part here is just, it says that the result of this is a temporary variable. And
So it turns the int into a Python?
so it turns the int into a Python object. It replaces this node with a node that wraps it with a coercion. And then it goes on its merry way, and then it sets the type of self to be a Python object. And then if this was, say, nested in something else, then it would go up and say, okay, I have a Python object here, what do I have here, figure out what my thing is, and go on.
So the entry into the symbol, the thing that says y is an int happens in the analyze declarations for the, or what?
Yeah, so what will happen is actually when you, it's actually I think in generate functions, the very first thing this does before parsing its body is declare all the arguments. But if I did like, for instance, I could do like that. Then what would happen here is when this statement was processed, it would say, oh, I'm declaring a variable y of type int. And then when it went through and analyzed the types of this, it would say, oh, I am looking for a variable y, found it here, and then do the same thing. If, for instance, I could have also this. And what would happen is at this point I would say, look up a variable y. Oh, I didn't find one in my scope. Go up to the enclosing scope, look up variable y. I found one, is type int, and do the same thing. So. So kind of related to that is the idea of temporary variables. So if you actually look at the source, you'll notice that the thing is just full of all sorts of variables that look like
The generated source. Or
yeah, the generated source.
Yep.
Looks stuff like this. Or this is a prefix that's put on so that things don't. Actually, I think it might actually, the V is for variables that are declared. So it's full of things that look like this. And these are temporary variables. So what happens, for instance, is this code right here. So if I write something like this, the actual C code that gets generated looks like, so actually, this would have to be like that. So either this is determined at one time or whatever, but this has to be an object representing the integer 2 that has to be created at some time. And then this was, for consistency, this is a y. And then actually out here, there is an error check to see if an error was raised, this thing will be null. And so this error says set some flags and jump down to whatever try except block is the surrounding block. The same thing here. And then it would do, for instance, and then it would have to do, for instance, like that.
Do you ever wonder if all the Python C API code that people like the authors of NumPy write is actually a lot less bulletproof than what Cython generates? I don't know, I've hardly looked at any such code, but there's every single time you do something like that, you should be checking the return value and doing all this stuff. But if you were writing, by hand against the Python C API, it would be immensely tempting in various cases to not actually check every possible return thing. You know what I mean?
I mean, it would be interesting if I fed, for instance, NumPy, an array of object, like say I made a vector of pi objects, and when I added them, like say it was a vector of rationals and a vector of integers mod 5.
It overflows.
If I added them, Sage would throw an error there. It would just be a normal error to say I can't add these two things.
Yeah.
I wonder if it would actually catch it, or if it would store the null value of the vector and then badness would happen later on.
Yeah.
So.
Or if you, does it check every possible exception?
Yeah. So I'm certain that, and also this kind of stuff what makes it possible to have tracebacks. For instance, you could imagine having some loop that goes through an adsmall and does a bunch of stuff. And then at the end it would say, did any errors happen?
Exactly.
But that won't give you very much information about tracebacks.
But it's easy to write by hand.
Yeah. So what happens here is every time you do anything in Python, lots of times temporary variables. For instance, to make a function call, what you have to do is you have to allocate a tuple and stick the arguments into a tuple and then make a function call on that. And this is all transparent. This is what happens in the Python interpreter, but it's all transparent to the user. You just think, oh, I have 3 arguments to this function. You don't think of the fact that you have to pack them all into a tuple to pass them off. So one of the things that happens in the analyze types phase is it actually allocates temporary variables. This is a pitfall. You have to allocate, what you do is you say, I need a variable. Then you say, here, I need another variable. And then you say, now I'm done with this variable, now I'm done with this variable. And you have to allocate, you have to say when you need variables and then release them in the right order. So that, for instance, you don't have 100 temporary variables, because you want to be able to say, use this temporary variable again somewhere else. I'm actually not sure if that's needed, because I wonder if the C compiler could figure it out. That, if I never use this variable again, then I can use that spot for this variable that I'm using for the first time, since everything's allocated on the stack. But that's not the way it works. And this way, at least you know it's happening correctly. And you do need to decref. For instance, if you didn't have this decref here, then this temporary variable that was y squared will be around forever when you exit your function. You need to free that temporary variable. So that's something to keep in mind. A lot of the complexities when you actually look at the function are due to this fact that you have to allocate temporary variables and then free them. So the other question that comes up a lot is, what's the difference between a PXI file and a PXD file? So PXI file, the I stands for include, and the PXD, the D is declaration. And probably one of the main reasons the PXI files exist is because they came along before PXD files. And so PXI file says, take this file and just insert it into my file, textually, like a copy paste. Versus a PXD file actually acts more like a module where you say, here is some things that are available. For instance, when you write a module and you want to be able to use it from another module, you write a PXD file that says, here's the types that are available, here's the CDEF methods that they have. And you can do this in a PXD file. And then it will, for instance, only get included once. Instead of getting, like if you say I have a class called A, if I do for instance, if I have this piece here, what will happen is it'll say this A belongs in the module lowercase a. Whereas if this was a PXI file and I included it, it would just textually include this piece here, and it would think that A is a class that I'm defining in this module.
So the Python C API PXI files that I wrote, should those all be PXD files?
So those should probably all be PXD files, yes.
Okay.
In retrospect.
How would you use, you would use them differently though? I mean, because you'd have to do a C import and then the functions wouldn't be there, they would be in the PXD, so you'd have a like extra scoping.
Yeah.
And
So
also
this-
with like GMP, you have to change all your code to have, or because there's no from pxd file import star.
So that's
so
the
to
thing
speak.
is, you would want to be able to do an
Is that
import
right?
star.
Yeah, so they really do serve a different purpose still. If you're just declaring a bunch
for
of C
each of
functions.
those PXIs that you're changing to PXD, you could then make a PXI that would.
Well, but the point would be to get rid of PX. I mean, the PXIs
Yeah.
I'm thinking of are things that declare the functions in the GMP library, for example. Like I wrote a PXI file by copying all the function declarations from the GMP documentation into a file, and then that gets included anywhere when you want to start using GMP functions. So you don't have to do cdef extern froms explicitly.
Yeah.
I don't see how PXD files solve that problem at all, unless they were
So-
from blah,
So there, so
from GMP import, C import star or something.
So there is there is motivation to do an import star at the module level, and that's one of the ways you'd want to use it.
Okay.
The other advantage it has is you could imagine, like right now, there was an error in decal.pxi that actually just caused a warning rather than making the compiler crash.
Yeah.
And I noticed when you're compiling stage, lots of files, if you trace it back, parse the entire decal.pxi
Yeah,
4 or 5 times.
Yep.
And that's per file in Sage.
Wait, why would the
That includes, for instance, the NTL stuff.
wait? Why would it do it 4 or 5 times per file?
Because the problem is, like, you have this includes where, like, you'll have a file that includes this file and includes, like,
And they
you
both.
have a function
I
that,
see.
you know, something that includes decal.pxi,
Uh-huh.
and you know, I also include something that includes decal.pxi.
Uh-huh.
But since it's a PXI, it'll just, you know, textually include it twice.
Right.
And in fact, it textually includes it more than twice.
Oh my god.
Everywhere.
And so that will really kill compile times. And the thing is, with a PXI file, there's no way to, you know, pick all the parsed version and then just load that.
Yeah.
Whereas with a PXD file, you can do stuff like that.
This is very relevant for interactive use also because, for example, when you do %Cython in the notebook, it includes a whole bunch of different PXIs automatically.
Yeah, yeah.
Like the GMP stuff, the
Yeah.
Python API, the GSL stuff, I think.
Yeah.
So that shift hinter, when you do it in the notebook, it's doing a lot of parsing. So
Yeah. And I
why
mean, I
can't
think,
it be cached in some way?
so that's the thing. If you do a PXI file, it can't be cached very well.
Okay, but a
Because
PXD could.
symbols might be different depending on where you're textually including it.
I see.
But a PXD file, hopefully you'd be able to cache it. And hopefully you'd be able to cache it once per, say, compile of Sage.
Yeah.
Where once I've already, you know, processed integer.pxd, I don't need to reprocess that for everything that C imports it.
Okay, cool.
So then 2 other things to just close up with. One thing is that there's an offset in the different phases. So when I'm parsing a function, the analyze types phase doesn't happen until later on of the inside body. And that's, for instance, because I need to, if I'm analyzing declarations, I need to analyze all the declarations in this module before I go into this function and analyze any declarations. And this can be something that you need to be aware of in the code, that once you jump inside a body, there's kind of an offset between the different phases. For instance, the actual trigger that analyzes the types inside a body is the generate code of the outside of the body. And there's some talk of making these more synonymous, but you can't make them completely synonymous because inside this body here, you should hopefully be able to call functions that are here without forward declaring it. So, and then the other thing that has to do with types is you'll notice that there's a lot of declarator nodes. And if you, for instance, print out a tree, it's like this really nested, deep thing of declarator nodes sometimes. And that's Cython's way of doing complicated types, like say if you have a foo star, like that. There will be a million declarator nodes floating around saying, I'm just declaring a name with, I'm declaring a pointer to a name. So sometimes, like, if you want to actually get out of that foo, you have to like descend into a couple declarator nodes because the actual node that represents this is just a node that says I'm pointing to something else. So that's something to be aware of. And I think this could probably be handled in a little cleaner way, because right now you have these really deep declarator node trees, and like the actual data is at the bottom, whereas you think of usually the name, for instance, being at the top, and then the typing information that's stored in the declarative node is an attribute of that. So kind of have to think backwards when you're doing stuff with pointers to things. And, yeah.
Okay.
Okay.
Any questions?
How do you
Hi.
print out a tree?
What?
How do you print out a tree?
So, look
Nope.
at,
Don't waste trees printing out trees.
Yeah, tell it to print 8,000 pages.
yeah.
Staple them together.
That's a tree.
So I would look at, DAG has some examples, maybe on the, where is the,
Wow. There's a lot of steps.
yeah, well, so
Jeez.
I had a bunch of ideas,
God.
and then DAG went and like turned all of them to SEPs.
Wow.
I mean, for one hand, this is like things that have been building up over 2 years. You know, people would like
Wow.
to see. But on the other hand, I think a lot of, you know, ideas just got turned into a SEP rather than just
We
being
need to do that
ideas
more
that
with
were-
Sage. I don't think we have any subs that are just sitting there.
Yeah, there was like calculus and number theory. I think we
Yeah.
only 2 so far.
Did the coercion model have a sub?
Yeah, I think it did.
Okay.
Yeah,
The notebook did.
the
No.
coercion model.
Well, that's
We don't have time for that.
So here is how you do it.
Okay, I see.
This four-range, you want to exclude this four-range optimization because that's actually broken. And I don't even know if it's included in Cython, so it might give you an import of it. But you just do the -t print tree. And it'll print out something like that. So,
Cool.
okay. So
Right.
any other questions?
Nope. Right. So next week.